Okay, so we have a function that we want to solve called equalSizes array, which essentially it takes in an array, as you can see. An array would be such as this, and there's an index. You want to find, is there a point in this array that is there an index that you can fulcrum off of, or like be everything to the left of that index? Um, all the sum of these arrays to the left would equal the sum to the right. So for instance, at the first array, or for instance, 0 index, first index, the sum of 1 is 1, and then you skip this one, and then everything to the right of this, the first element, or element with the index array, or the second element, if you sum all of these together, will equal 1. So if you keep on going through, if you, like, I like the physics term of a fulcrum, you know, with like a teeter-totter. Like if that's a teeter-totter going up, you have this little thing, what's it called? A bounce, that's the fulcrum, I don't know, that's what I used in this. So I saw it, put this middle index or index fulcrum index, if you do it on this, so if you add 2, 3, and 1 together, equals 2, 3, 1. So that's true, and what you want to do is return the index of this number, so it'd be 0, 1, 2, 3. So you would return 3. Essentially that's it, and if it's not possible to find a balancing, it's kind of like a teeter-totter in a way, and each is a fulcrum. But if there isn't one, then you just return -1. So that's kind of the idea. So at first I thought maybe a divide and conquer point would be good. Just find the middle point and just keep finding the middle point until you don't. And if it's larger, if the sum is larger on the left side or the right side, then you move the fulcrum that way. But that was wrong because divide and conquer kind of helps with, it's really lends itself to ordered data, and this is still not ordered. This could be any range of mixed unordered data. So then I just thought general intuition is just for loops through each element in the array, and then you just add up everything to the left and to the right. But that's inefficient because you keep on summing up other prior calculations. So my thought process was you just start off at the second element here. You sum up everything. Since we're not using this, we can have initialize this to the, like I call it, to the fulcrum value. So fulcrum val is equal to 2, and then everything. Then you have a left sum and a right sum. So all you gotta do is sum it once. So this is your initial statement or initialization. So your left sum is equal just to 1, or the first element, and then you just sum up all the rest of them to the right. And if that doesn't work, then you're just going to add this fulcrum value to the left sum, and then you want to subtract 3 from the right sum. So then you get 3, and this next iteration you have 3 is equal to this, you know, and that doesn't work. So then you move the fulcrum value again to 4, and then you would add 3, which was the prior fulcrum value, to the left sum, and then you subtract the first element from the right sub, and then yeah, just keep going until you find that. And then that's a big O of n instead of n squared, just doing it, looping over each one and always finding left and right side value. So to iterate that in, to implement that in code, you take your left sum, like you said, you initialize the left sum is just going to equal the first, actually this could be just be 1, 2, and then your right sum is going to be your third element all the way to the end, and this is just a reduce function that sums it up. So you initialize your left sum and your right sum, and then yeah, you just start for looping it, starting at that first element. So and then you always keep on changing what the fulcrum val is whatever it is at that point where you're iterating over. And if you ever do find that left sum and right sum equal each other, then you just return that index. If not, you just want to, every time you iterate, you want to add the fulcrum value to left sum and then subtract the first element in the right sum, which is going to be the array plus the next, the one to the right of it. Because if this is your, if three's your, if you're looking at 3 and that's your teeter-totter point, your fulcrum, you want to subtract 4. So this would be I, and then this would be I plus 1. And then and then loop through over it. And if your for loop doesn't have a return, they just return -1. So then if you just node these two out, the first one, maybe this has to be 0. Yeah, there we go. So as you can see, this one doesn't have a solution of a teeter-totter that balances out, but this one does on the third element. See? So 1, 0, 1, 2, 3, yeah. But yeah, that's kind of how that works. Yeah, so essentially, I have to think, speaking it out, it's kind of like a teeter-totter. And you just gotta find the balancing act, and yeah, the trick was to get a 0, or to say a constant or linear time, big O. You sum up all at once, and you just continually add the left sum, that's fulcrum value, and subtracting the first value from the right sum. Pretty fun.